If we choose a different lemma right here than this one, it turns out to lead us towards a different but also correct algorithm. Instead of considering when we want to get from dx to y, everything that ends up at y, let's consider everything that starts at x. From x, we can always get to its immediate neighbors v, and if we have figured out the minimum to get from v to y, then again we know the minimum to get from x to y. As long as we know all of those v's that we can reach from x, we can pick the smallest one. This is called the Bellman-Ford equation, and the Bellman-Ford algorithm builds on this. Instead of only starting with final answers, where we know when x and y are the same, the distance from x to x is 0, we're going to start with estimates of answers and refine them towards the actual minimum. That is, if you're trying to get from x to y, we know at least you can do it with cost c if x and y are immediately connected. If x and y are not immediately connected, then we don't know yet. It's some number of steps, and we can just use infinity as a placeholder. But now we go into this loop, where if we've observed that x and v are adjacent, and we know that cost, and if we have an estimate so far of getting from v to y, then we can improve our estimate of x to y potentially. If the connection from x to v plus the distance from v to y is better than our current guess at x and y, then we'll refine our guess and we'll get closer to the correct answer. So we only update when things get smaller, so we must be moving in the right direction. Also, we're going to run out of these steps eventually, and that's because every time we update, we decrease by a certain amount. The smallest we can decrease corresponds to the smallest difference between two edges, so that is a fixed number that we could only subtract so many times to hit 0. We're probably not going to hit 0, so that means we will stop somewhere. And that means it's going to stop everywhere, and so we will eventually arrive at the right answer.